Hi everyone, I'm Evan from nTopology. I'm a senior applications engineer here, and I'm going to be showing you our new latticing technology. The new latticing technology introduces a consistent architecture and workflow for lattice creation. The new blocks provide greater control for lattice creation, enabling higher performing parts and a wider variety of designs. With the new latticing technology, it makes it easier to learn and use. Because we've broken it up into the three fundamental elements of lattice creation: the unit cell, the cell map, and the parameters of your lattice structure, such as thickness. Let's take a look at the first part here, which is going to be these unit cells. The unit cell, being broken up into its own individual component, gives us this ability to visualize it separately. So now I can take a look at this drop-down list that we provide inside of nTop, and we can change things up. If we want to look at different unit cells, we can look at them as a graph representation or an implicit representation. We can use this slider here, and with our GPU acceleration, we can get a visualization of different thickness values on our lattice structures. We're able to very quickly and easily visualize the changes in the unit cells we want to be able to use. Whether it's a graph unit cell, a walled TPMS, or a standard TPMS, we have this easy visualization available to us. Not to mention that we've also broken up these cell maps into their own individual components. So let's take a look at one of those. What I'm looking at here is a rectangular cell map. Now we have a multitude of different types of cell maps. We're going to look at a few of them here. But this rectangular cell map, if I open it up, we can see I'm choosing the volume that I'm infilling, which is this cube, the cell size, I can control the frame, I can control every single thing about how I want to map my lattice structure here. And we didn't stop at things like rectangular. We also have cylindrical cell mappings. We have spherical cell mappings. We have conformals. We have surface conformals. We have quad meshes. There are so many different ways to control your cell maps here, giving you even more power than you had before. Now, when we put all of that together, we're able to create our lattice structure. And we're looking at a rectangular mapped lattice structure here with a beam-based unit cell. As you can see in here, I have my beam unit cell, I have a rectangular cell map, and I have my thickness applied here. And if I want to make the change to anything, well, I just go to, if I want to change the unit cell, I go up to where my unit cell is, and I make a change here from body-centered cubic to face-centered cubic. If I want to add in more unit cells, why don't I change the size of my cube? So from 10 millimeters squared to 20 millimeters. And now we're getting these new lattice structures on our screen in an extremely short amount of time, right? These are taking advantage, an extreme advantage of our GPU acceleration, giving us lightning fast lattice generation. Why don't we take a look at this in context of a real part? Now looking at this bracket, we have this nice lattice infill with our new lattice architecture here. And it couldn't have been easier to create it. And not only couldn't it have been easier to create it, it can't be any easier to make changes to it. Let's say this rectangular cell mapping that I have inside of here right now, I don't really love it. Maybe I want it to be cylindrically mapped. And I take a look at that and wow, that doesn't look quite too great with a beam-based lattice structure. What if I wanted to do a TPMS lattice structure? I can just swap that right on in. Because of this new architecture, it gives me this freedom of design. We can map it spherically if we really wanted to, or we can even do things like conformal cell mappings as well, and we want to swap it back to a beam-based lattice structure. We can continuously make changes to these lattice structures without any worry throughout the process. We can even incorporate field-driven design. So let's say I have some high stresses in some locations, some low stresses in some locations. Of course, that's still incorporated into this lattice generation. I put in my field for my control system here, and now I have a variably driven lattice structure just like that. All of this is what's making it faster and easier to explore your design space and even run things like a large design of experiments to find the best part possible. Switching over to a new file now, I want to talk about how not only can we use field-driven design to modify the lattice's parameters, we can use field-driven design to modify the lattice's cell map itself now. So let's take a look at this shoe file here. What we have going on is a variably driven lattice structure to put more support where we have higher pressure in our shoes. If we take a look at this, I'm starting out with a uniform cell map. Let's get a top-down view of this to really get the full understanding of what's going on. And if we take a look, I have brought in some external data. So I have areas of high pressure, areas of low pressure. Now, traditionally, what we might have done is utilize that to change things like a wall thickness or a beam thickness or something along those lines. But what I want to do now is I want my unit cells to be smaller in the areas of high pressure and larger in the areas of low pressure. Now we're able to do that. If we take a look at this, I can go ahead and swap from a uniform cell map to a variably driven cell map with smaller unit cells in the areas that I want them and larger unit cells everywhere else. So not only are we able to go ahead and create these variably driven lattice structures with things like parameters, but now we can actually physically control the cell mapping itself as well, which is just a new capability that we've introduced to give you more power along the way. Switching files, let's also switch topic from volumetric lattices to surface-based lattices, because we've also created a number of improvements for our surface-based lattice structures. One fantastic example of that is this topology optimization bracket here. We have a very nice optimized geometry, but what we want to do is actually add in some more strength to it without adding a lot of weight. And the way we want to do that is with some structural ribs, right? Now this is pretty complex geometry, but we now have a technique where we can map lattices to any geometry that we want. And I'm going to do that through the use of a quad mesh. So I'm going to toggle on my quad mesh here. If we take a look, I have a quad mesh running over the optimized portion of my geometry. And we have this new form of cell mapping here called cell map from quad mesh. And what this allows me to do is lay a cell map actually on the quads of my mesh here. And with this capability, this allows me to do things like adding in structural ribs to complex topology optimization geometry. No matter how complex it gets, we can utilize this technique to add in some extra strength without adding in a lot of mass because of this new architecture. The improvements in our lattice technology expand beyond just periodic-based lattices, even into our stochastic or Voronoi style lattices. These lattices have been improved in similar ways, such as speed and ease of use. But some additional improvements have been made. Taking a look at this ALIF implant here, we can notice that we have a nice stochastic lattice, which is really fantastic for things like osseointegration. And the design and control of this couldn't be any easier. If we take a look, all I have to do is define seed points, a thickness, and an optional mesh. Now, that optional mesh will allow me to do things like capping off the ends of this lattice. That is an optional input, however, and if we take a look at our lattice on the inside here, we'll notice I'm also able to apply field-driven design to these structures. But my favorite improvement comes from the properties. If we take a look at the properties of these Voronois, we'll see a new one here called cell diameters. And that is measuring the diameter, or essentially the effective pore size, of each of my structures. Meaning I can do things like calculate the minimum, maximum, or even the standard deviation of these cell diameters, allowing me to control the design. So if I'm designing to osseointegration, I can ensure that I'm well within my parameters thanks to this new property. If you want to learn more, go to our support page. We have an extensive technical document and extensive technical FAQ on our new latticing technology and how to transition to using our new latticing tech.